Okay, so next section, you're going to want to try to tackle without a calculator. So we always want to factor first. So the first thing we're going to do here is factor our numerator and denominator. In our numerator, we can factor out 3 as a GCF. In our denominator, we can factor out a 6. So when I factor out a 3, I'm left with x squared minus 6x minus 27. And in the denominator, when I factor out a 6, I'm left with x squared minus 9. And then those are nicer factoring situations now. Much nicer to find that GCF first. 2 numbers that multiply to negative 27 and add to negative 6 are negative 9 and positive 3. I'm just going to double check that those signs all make sense. Good. Okay. And in the denominator, I have that 6 out front, and then x plus 3, x minus 3. So there's our non-reduced guy. I'm going to go ahead and cancel here. That means I'm going to have a removable discontinuity at x equals negative 3. So I'm going to put that down here. So my reduced fraction is 3 times x minus 9 over 6 times x minus 3. Okay. Here's what we got. X-intercepts come from the numerator and just our x's. So that x minus 9 is going to give us an x-intercept of 9, 0. The other thing I can pull, the other 2 things I can pull just from what we got going on here are vertical asymptote comes from the denominator, that x minus 3. So a vertical asymptote is x equals 3. And then our horizontal asymptote comes from the relationship between the top and bottom. These are the same degree, x squared over x squared. 3 over 6 reduces to 1/2. We're always writing those as equations. You're not going to get credit if you don't write those as equations. We have a horizontal asymptote. We don't have an open. We're super close. The 2 pieces of information that we still need, well, we're going to do domain and range, but the 2 pieces of information we still need are the y-intercept and the removable discontinuity. And we get those from plugging in to our equation. So I like to just do a table here, and we can plug into the reduced fraction. Our y-intercept is where x is 0, so we need that. And our removable discontinuity is where x is negative 3. So those are the 2 pieces of information just plugging in. So 3 times 0 minus 9 over 6 times 0 minus 3. 3 times negative 9 is negative 27. 6 times negative 3 is negative 18. 9 goes into both, so 9 divided by 27 is 3 over 2. So that's our y-intercept. And our last little piece there is the y value of our removable discontinuity, so we'll plug in negative 3. So negative 3 minus 9 is negative 12. Negative 3 minus 3 is negative 6. So negative 36 over, negative 36, positive 1. Domain and range, last pieces. For domain, we're going to exclude our vertical asymptote and the x of our removable discontinuity, least to greatest. So negative infinity to negative 3, negative 3 to 3, 3 to infinity. If you're doing that in set notation, or if you're asked for that in set notation instead, x such that x cannot equal negative 3, x cannot equal 3. For range, we're going to exclude our horizontal asymptote and our y value of our removable discontinuity. So negative infinity to 1/2, 1/2 to 1, 1 to infinity. Or y such that y cannot equal 1/2, y cannot equal 1. All of that without touching a calculator. Just be prepared, especially in factored form or with easy factoring like this, to be able to answer some questions, especially about asymptotes and zeros. Those are really important. Those are things that you should be able to identify and write out, whether you have a calculator or not. All right, let's go ahead and do one more on this video. I think we can fit 2 on here. Same deal, I'm not going to touch my calculator, and I'm going to start by factoring. So this factoring situation, I can cut in half on top. Anytime you have 4 terms, you're going to look for that factor by grouping. X cubed minus 6x squared, I can take out an x squared. Ooh, 3x minus 10, or 3x plus 10, I can't take anything out there. See, if I switch things around, I don't think factoring is going to be possible in the numerator. So let's factor our denominator. Negative 4, 2 numbers that multiply to negative 4 and add to positive 3 are positive 4 and negative 1. All right. I could try to switch the order. Sometimes if you switch the order of the middle terms, it's helpful. If I switch the order of the middle terms, I'm able to factor a little bit, but the factoring doesn't get me anywhere. It doesn't, I'm not able to break it down into 2 separate steps. The reason I'm thinking that's going to be okay is that I'm going to have an oblique asymptote here. So, since I have a top-heavy fraction. So let's get through as much as we can, and if we need to double check anything, or if you want to pull up your calculator so you're a little more comfortable, you can absolutely do that. Let's start with our asymptotes. Since nothing's going to cancel, our asymptotes come from the denominator. Here I have 2, x equals negative 4, and x equals 1. Our horizontal asymptote, we're not going to have a horizontal, we're going to have an oblique. And that's going to come from doing some synthetic division. So our synthetic division here, we're going to set the top as what we're dividing, and we're going to divide by our vertical asymptote. So I'm going to start by dividing by 1. And remember, when we're doing synthetic division, we just take those leading coefficients. Multiply here, 1 times 1 is 1. Add vertically, negative 6 plus 1 is negative 5. Multiply 1 times negative 5 is negative 5. And then add here negative 2. And remember, we don't care about our remainder. Now, I started with x cubed, so this guy here is really 1x squared. For our oblique asymptote, we're looking for a line, so I need to divide again. And I'm going to be dividing by my other asymptote now. So since I already used 1, now I'm going to use negative 4. Now my 1, multiply 1 times negative 4 is negative 4. Negative 5 minus negative 4 is negative 9. So that I took myself down by dividing twice. I took myself down from an x cubed to a single x. So that's y equals x minus 9. Lovely so far. Let's find our other pieces. Okay, other pieces that we need. I don't think we're going to have a removable discontinuity since I can't factor, but we will take a look at that once we kind of get our numerator dealt with. A y-intercept we can definitely find by plugging in 0 for all of our x's. So let's go ahead and get that taken care of. So the little table helps you here. And if you look at the way the numerator works here, all of our, the only x that matter, or the only value that's going to be left when we put the zeros in for all of our x's is that 10. So we're going to end up with 10 over 0 plus 4 times 0 minus 1. So that's going to be 10 over 4 times negative 1 is negative 4. 10 over negative 4 reduces, 2 goes into both, so 5, 2, and it's negative 5 halves. So our y-intercept is negative 5 halves. So the numerator is tricky on this one since it's not factorable, and I definitely wouldn't do that to you on a test if it was a no calculator problem. The thing I will tell you right now is if you put this in your calculator, one of our x-intercepts is at negative 1. And you could do rational root theorem I know you guys remember that from Algebra 2. If you were really in a bind, you could do rational root theorem and double check that. Your others are 5 and 2. Those are our 3 zeros. So 5, 2, and negative 1. So again, I just got those zeros from x-intercepts from putting that into my calculator. And actually, before I print this, maybe I'll go ahead and write that guy in factored form for you. Removable discontinuity, we don't have any, since our factored form of this cubic would look like this: x minus 5, x minus 2, and x plus 1. So nothing cancels. Domain and range are going to be a little easier on this one. Domain, we're only going to exclude our 2 vertical asymptotes. So negative infinity to negative 4, negative 4 to 1, and 1 to infinity. Or x such that x cannot equal negative 4 and x cannot equal 1. Our range on this one is actually all reals. If you pull that up on your calculator, which I encourage you to, you can see that you have this little guy that kind of looks like a cubic, like a reflected cubic that goes through the middle of your graph, and it crosses that asymptote. So it's a weird one. We have a range of all reals, y such that y is an element of the real numbers. All right, so those are 2 problems we didn't need to graph, but we did found all of the other pieces.